My name is Emma Frid, and I'm presenting the paper Mapping Inter-Cardiovascular Time-Frequency Coherence to Harmonic Tension in Sonification of Ensemble Interaction between a COVID-19 patient and the medical team. And this is work that I did together with my co-authors Michele Orini, Gianpaolo Martinelli, and Elaine Chu. This project focuses on sonic and visual representations of heartbeats of a COVID-19 patient and medical staff treating the patient. The aim of the work was to sonify heart signals to reflect how the medical team comes together during a COVID-19 treatment. We investigated heartbeat rhythms of 5 medical team members and the patient, as well as time-frequency coherence, TFC, between the patient and the medical team's heartbeats. With this work, we aim to highlight similarities between heartbeat signal analysis and audio signal analysis by mapping intracardiac time-frequency coherence to harmonic dissonance in music. Our work is based on the idea that heart signals can be readily mapped to music, since music and heart signals share several common characteristics. The idea of drawing parallels between music and heart signals is not new. Academic physicians wrote about the music of the human pulse as early as in the Middle Ages, and physiological measures such as respiration, blood pressure, and heart rate have been shown to increase and decrease with tempo. The similarities between the human pulse and music means that heart signals can be mapped to music. For example, arrhythmias and other heart conditions can be considered as highly musical, based on their innate periodicity and time-varying musical structures. Previous work on sonification of cardiovascular features has largely focused on electrocardiograms, so-called ECGs. An ECG is a visual representation in the form of a graph that depicts voltage versus time of the electrical activity of the heart. This is usually measured using electrodes that are placed on the skin. A common way of assessing activity of the autonomic nervous system is to analyze the heart rate variability, or HRV. HRV corresponds to the degree to which the time interval between successive heartbeats fluctuates. In the analysis of HRV signals, the estimation of spectral coherence, that is, the degree of correlation between the spectral components of two signals, can be used to assess coupling between two individuals' heart signals. Our framework for heartbeat sonification is based on calculating TFC from ECG signals and to map these values to harmonic tension. For more information about calculating TFCs, please refer to our paper. After computing the TFC, we synthesized 6 voices of sounds that portray the heartbeats of the patient versus the medical team members and visualized the results. We used data from Holter recordings that were collected from 1 patient and medical team members who were involved in the ward round in the COVID-19 intensive care unit in the UK. Heart rates in beats per minute of the patient versus the medical team are visualized in the figure in this slide. The patient in question had a heart transplant, meaning that he had a faster heart rate and low heart rate variability compared to the medical team. We mapped time-frequency coherence of the heart signals to harmonic tension in the spiral array, which is a model for tonality in the form of a 3D representation of pitch classes, chords, and keys. In the spiral array, each pitch class is represented as spatial coordinates along a helix. Notes that are sound tonally close are positioned close to each other inside the array. 3 methods for quantifying aspects of tonal tension based on the spiral array are presented in the work cited in this slide. One of them is the cloud diameter, which captures the largest distance between any 2 notes in a cloud. If a cloud of notes contains intervals that are dissonant, that is, tonally far from each other, the distance in the spiral array will be large. In this way, Euclidean distance within the cloud can be used as a measure of harmonic tension. This figure describes the workflow from data to sound synthesis. Heart rates of different persons are used to trigger sounds. Each heartbeat triggers a note. In total, there are 6 simultaneous voices in the sonification, 1 per person. The pitches for the patient were predefined and inputted to a Python script. A rule-based system was then used to map TFC values to notes for the medical staff members. We explored a range of different sound models using this mapping. The ones included in the paper are synthesis of glockenspiel sounds and sampling of pitch-shifted cello plucking sounds. The rule-based system allowed us to map distances between pitches in the spiral array based on average TFC values between the patient and each medical team member. High TFC values resulted in pitches located far away from each other in the spiral array, that is, more dissonant pitch combinations, whereas low TFC values resulted in pitches close to each other, that is, more consonant pitch combinations. In order to further highlight the rhythmical structures of the heartbeats and TFC changes over time, we also created a visualization of the sounds using processing. The visualization was designed as a 2D display in which each person is represented by a square on a dedicated row. The patient square is displayed at the top, with medical team member squares situated below. For every heartbeat, the squares move a step to the right. TFC between each person in the medical staff and the patient was mapped to a blue component of the color of the square. Greater TFC resulted in a color that was more similar to the red hue of the patient square. We conducted a web-based auditory-only listening experiment to evaluate if the proposed sonification framework could be used to successfully communicate time-frequency coherence through sounds. For this purpose, we created 10 stimuli pairs divided into two categories, coherent versus non-coherent. These two categories consisted of sound files created by data excerpts with an average TFC below versus above a predefined threshold. The participants were asked to listen to 10 pairs of sounds and select which one they thought came from the most coherent signal. For clarity, we only played the sonification of the patient and a single person in the medical team, not 6 simultaneous voices. Pooling the data across sound models and stimuli resulted in an overall accuracy of 69%, which was significantly higher than chance. In other words, the participants managed to distinguish between coherent versus non-coherent sonifications rather accurately. However, qualitative findings indicated that the rhythmical structure of the heartbeats may influence how the sonifications are perceived, in terms of communicated coherence. To conclude, we have presented exploratory work focusing on mapping time-frequency coherence measures of the heartbeats of a COVID-19 patient versus persons in a medical team to notions of harmonic tension in music. Results from our listening experiment suggested that the proposed framework was successful when it comes to communicate low versus high time-frequency coherence. For more information about this work and other work on heart signals and music, please see the Cosmos webpage.
I believe we have our first question. Can you comment on why you chose to represent what seems to be a rhythmic-related phenomenon using pitch-based auditory dimension, like harmony?
You mean why we decided to portray it with pitches instead of rhythmical?
I believe that's the question, and which implied also some harmony. I had a similar question because your non-correlated example had inharmonicities also in it.
Yes, so it's a good question. We of course there's a lot of rhythmical stuff going on here, but we wanted to focus on a mapping in the spiral array. So the kind of premise of the work was to work with tonal tension, and so that's how we just kind of started the project. But then of course the combinations, there are a lot of different temporal combinations of different heartbeats within this group, and the data set is 64 minutes. So there's a lot of temporal stuff that you could also, of course, go into and investigate more in detail.
I think as a follow-up, when you're monitoring multiple patients at the same time, you mentioned up to 6, does that build up in the harmony? You're using different notes for its patient. How does it work?
So it's based on the fact that you have like a foundation of like a set of pitches for the patient, and everything is in relation to the patient, which means that the time frequency coherence is always calculated in relation to the patient. So between the different doctors and nurses in relation to the patient. And so the pitches are calculated based only on the original pitches of the patient, which means that if you add them on top of each other, they're the kind of it's only going to be in relation to actually what is the coherence to the patient. Of course, you could have calculated also the relationship between the different persons in the medical team, but then that would be another sonic representation.
I'll abuse my role and I will ask another question while people are typing. I've noticed in your presentation and your paper also, you're using quite a few different tools, MATLAB for one thing, Python for another, Sonic Visualizer. Can you comment a bit of that and on the choices of the tools?
I think that the choices of the tools is as a result of the fact that it's a collaborative work where we are pretty multidisciplinary, because of course there are different parts of this. First is doing the analysis of the heartbeat signals, and that's why that was done in MATLAB, because it's one of the collaborators who works in that kind of framework. And then we did things sequentially, moving maybe from the tools that we are most used to using and to the very end. So it was a mix of different persons doing different things. And yeah, that's probably why it ended up being so many different things.